الأمريكية. طبعا كما تعلمون اليوم المؤتمر بيغطي منحيين مهمين في هذه الجلسة. الأول بيتعلق بالسايزميسيتي والثاني بيتعلق بالستراكشرال هيلث بيرفورمانس. وأنا بعتقد إنه هذه المواضيع هي ريليتد لواقع قطاع الهندسة بالأردن ولواقع بلدنا. وأكيد إحنا شفنا خلال الفترة الماضية مشاكل بتتعلق بالستراكشرال هيلث مونيتورينج، وإحنا أصلا موجودين بمنطقة قريبة من حفرة الانهدام، وبالتالي موضوع التأثيرات الزلزالية والتأثيرات التكتونية اللي ممكن تأثر على المباني واللي بنأخذها باعتبارنا عند تصميم المنشآت المختلفة شيء أساسي وشيء حيوي. وبالتالي جاء يعني منظمي المؤتمر حرصوا على أن يكون في هنالك في جلسة متخصصة لهذا الموضوع. الآن اسمحوا لي أو allow me to shift in English. My name is Mohammed Abu Afife. I am a civil engineer, and today we have two keynote speeches. One is related to scientific resilience of concrete structures of building and building collapse performance for Dr. Halil Sezen, while the other will be delivered by Dr. Khaled Al-Shibli on the subject of infrastructure health monitoring opportunities and challenges. Our first speaker will be Dr. Halil Sezen from the States, and allow me please to give a short biodata or an introductory about his experiences. Dr. Halil Sezen is a professor of structural engineering in the Department of Civil, Environmental and Geodetic Engineering at the Ohio State University in Columbus, Ohio, United States of America. He received his PhD from University of California at Berkeley in 2002 and his master degree from Cornell University in New York. And of course, his BSc from the Middle East Technical University, Ankara, Turkey in 1993. His primary research interests are in performance evaluation of structural components and buildings using computational simulations and experimental testing. He investigates the usage of advanced material to reinforce, repair, and improve the performance of concrete structures. He is also the author and co-author of more than 150 technical and conference publications. He advised more than 50 PhD and master students, and he is a Fulbright scholar. Dr. Sezen is a fellow of the American Concrete Institute and fellow of the American Society of Civil Engineers, Dr. Sezen, the floor is yours, and you have 45 minutes to deliver your speech. Please.
Okay, thank you for the nice introduction. So today I will be talking about reinforced concrete structures and their response under seismic loads and extreme loads. It's fine, right? And let's get started. I will try to address these questions as much as I can. I will try to make it as less technical as possible. There are a couple equations here and there, but I will try to make it as simple as possible so that everybody can get something out of this presentation. So the main questions that I will try to address here is what are the contributions of different components to overall structural behavior or collapse? Why do our structures collapse? Do you think the slab or beam or column or foundation is affecting our response? And how do we quantify? And we will be looking at some extreme events or past earthquakes, what happened to those structures. They are very valuable for us. And then we will try to look at code requirements. Some of the seismic code requirements are very strict, and we will try to see why that may be the case. And one question that we still don't understand or answer is what happens to a building if you lose a column or two? Is that building going to collapse or not? So we still cannot answer that question. Sometimes it collapses, sometimes it doesn't. That's my research area for the last several years. And the last question is resilience. Resilience means if something happens to your structure, or community are you going to be able to come back to the conditions before the event. So I'm sure you have seen this picture. I was just looking at the location of Jordan and see how seismic it is, and most of your cities are very close to the fault line. We don't know when, but at some point it is likely that there will be or there may be an earthquake in Jordan. So that's quite relevant for what we are talking about here. After major earthquakes, institutions, at least in the US, send people or experts to the disaster areas. So there's a hurricane coming right now to the US, and they are already making plans to send investigators about learning what happens to those structures after wind or flooding. Similarly, after an earthquake, ASCE, FEMA, or in this case, Earthquake Engineering Research Institute, send experts and try to learn from what happened in the field. So this is one example that they put in their report where it says you have two identical buildings right next to each other in the same development. One of them has no damage, the other one lost the first story. And in the caption it says two buildings are almost identical. One of them is still standing while the other one collapsed. So these are the pictures that I took many years ago when I was a graduate student. So these two buildings are from Turkey, and during that big earthquake, one of them collapsed, the other one is still standing. So it looks like the contractor was the same, engineer was the same, materials seem very similar. They were almost similar structures, but one of them is still standing with almost no damage, while the other one collapsed. As I said, there are many, many examples. I pulled out another one here from Japan, where this building has no damage versus the other one lost the building. So now the question is, what is going on? So there may be answers saying, oh, maybe soil conditions are different, but actually they are not. Maybe minimal or ground motion is similar, all conditions seem similar, but one of them is collapsing, the other one is not. So the question is why that may be the case. It turns out these structures are behaving elastically. So if the earthquake magnitude or force is not large enough, nothing happens to the structure. It is like black and white. If the demand or the force during the earthquake is larger than the capacity, the building collapses. So it is either fail or no fail, no in between. And this is highly undesirable in our codes and standards. This is the response that we want. So after an earthquake, if it is large enough, we like to see a lot of damage in our beams and columns, but no collapse. This is just the opposite. So again, if you follow the modern or current guidelines, this is the response we want. So if we reach the limit, instead of seeing sudden collapse, we like to see some ductility. So how do we achieve that? That ductility is extremely important, that you will just keep hearing me during my presentation. So if this is a typical building structure under lateral loads, either because of wind or earthquake, what we do is we figure out these forces depending on the soil and the distance to the fault line and all those factors, and then we do structural analysis, and then first we design the slabs. When we design the slabs, we don't look at the lateral forces. It is mainly the gravity load, like we sit on this floor, or sometimes it is just a sound or vibration, and it has nothing to do with the lateral forces. So that's the reason our slabs are typically very rigid. So they act like a plate. And then when we transfer these loads to the structure, the first members that we look at are the beams, and we have to look at the bending and shear forces, and then we transfer the loads to the columns and then design the columns, or if we have walls, we design the shear walls and then transfer the loads all the way to the bottom. So I have a very quick question, although we have limited time. Since I'm teaching in classes, I always ask questions and then ask these questions in the quizzes. So, okay, everybody, if something happens and if there's a blast or something, and if you lose this beam, do you think people up there will be affected? Or if something happens and if you lose these two beams, do you think people will up here will be affected by that damage? The answer is no, because this beam or this beam is carrying the loads only in this floor. So if you look at that beam, it is carrying the people only here, not upstairs, not above our location. So that means during an extreme event, if we lose a few beams, it is not that bad because you will be only affecting people here, not up there. Let me ask you the same question. What happens if you lose this column? Do you think people will be affected up here? Or if you lose 2 columns, do you think people will be up there? I already hear from structural engineers. Yes, but in general, if you lose 1 or 2 columns, you are carrying the loads all the way from up here. If you lose 1 or 2, 3 columns, it is very likely that you will see partial collapse. The point that I'm trying to make here is one of the basic philosophies of seismic design, which is strong column, weak beam. So we intentionally like to make our columns strong and beams weak. So if we lose a beam, that's okay. Well, that's not okay, but if you push the structure to its limit, we like to be able to lose beams rather than columns. If you lose a column, your structure may collapse. If you lose a beam, it will be local failure. So that's the reason if you are doing a good design, you like to make your beams weaker and columns stronger. These pictures are from Japan. They are exposed, and you can clearly see that the beam capacity is smaller, or if you look at here, beams are smaller than the columns. That's all intentional if you look at the details. So what happens if we don't achieve that? So if you look at this parking structure, you have a huge beam versus relatively small columns. Same here. So during an earthquake, you see you push all the damage to the columns, and this is almost on the verge of collapse. So you already got 2 major ideas that we can use everywhere. So we like to make our structures ductile, a lot of deformation capacity before it fails. We don't want to see, boom, a brittle or sudden failure. And the second concept that we just talked about is strong column, weak beam behavior. These are the major philosophies of seismic design, and we like to make our beams continuous. We don't want to see separation, and then we like to use concrete shear walls as much as possible. Although they may be expensive, it is well worth it. So how do we achieve those concepts in structural design? So if you have a standard gravity load design, this is perfectly fine if you are not expecting large seismic forces where you don't need to use shear reinforcement, transverse reinforcement inside the columns. You see, you can cut your bars near the bottom. It doesn't need to be continuous. Sometimes you don't even need to come here. You can cut your bottom bars down here. And what else? And then spacing of the ties can be quite large, and you don't need to confine. So this is okay as long as your loads are always under gravity or vertical direction. But in a seismic or critical structure, this is what you need. You need a lot of transverse steel in the beams, transverse steel in the joint region columns, and then you cannot have those lap splices in these regions. They are very critical. So just to move on, even these very small details are very, very important. So I didn't have enough time, or I didn't spend enough time in Jordan, but I would assume in many cases, if you have a beam or column, you will have these 90-degree hooks there, versus in seismic design, you want these 135-degree hooks. So they may seem so little or so unimportant, but in reality, they are extremely important because during the cyclic loading, these 135-degree hooks are going to hold and confine your concrete. They are so critical to your design, even such minor differences on the surface will make a huge difference. So again, if you don't follow those rules in the beam column joints, that this is what happens. If you don't have that transverse steel that I was showing you, then you will see all these failures in your joints, and these are more examples. By the way, all of these examples are not out of blue. So there was an earthquake in Taiwan, I believe, about 10 days ago or so. If you go to the pictures, you will find this. There was another one, I think, 1 or 2 weeks ago in Mexico. So if you go to news and check collapses, and many of the failures and the collapses are in concrete structures, that's where people die. And in almost all cases, these are the failure modes that you will see. Columns failing and building collapsing, and you have these beam column joints. Here's a very good example. Japanese standards are very tight, as you can imagine. And this building was designed following these modern guidelines that I was talking about. So they were very strict, and they designed this structure. A few years later, or a few years after this building was constructed, Kobe earthquake happened, and they had to get rid of this, demolish this building. Although everything that this building experienced is what we want. So it was very ductile, as I was telling you earlier. They had damage at the ends of the beams, and then they had limited damage in the columns, and these cracks in the beams extended into the slab, and they had this type of damage in the lower floors. But as far as the building is concerned, it was perfectly fine, other than this type of damage that happened during the earthquake. And this is exactly what we want. But at the end of the day, they had to get rid of this building and put a new one. Can you think of a reason why they will get rid of a building that's only 2-3 years old? It's a practical answer. The answer is somebody has to go in there and fix all of these cracks, right? And maybe the steel yielded, they have to replace it, and they have to fix the slab. It was way too expensive to fix all these beams and columns, rather than getting rid of the building and putting a new one. That's what they did. So economically, it wasn't feasible. So where I am getting at is around the world, maybe except for Japan and Chile, a couple other countries where the earthquakes are so frequent, including Jordan and the US and Europe and China, everywhere, we design our structures. When you follow your design code, I'm not sure whether you're aware of it or not, so, clearly the owners are not aware of what we do. So what we do is, when we design our structures, our goal is to prevent the collapse of the structure, and we call it life safety. So we don't want to kill people. As long as people, see in this building, if a major earthquake happens, and if all these beams and columns are cracked, and the building is leaning by 1 meter, as long as it doesn't collapse, structural engineer is good. We did our job. But if you talk to the owner, they will say that's a terrible performance, because there's a miscommunication. So we are targeting collapse prevention or life safety. That's what the design codes are saying. So if you follow the codes at the maximum level, you cannot allow the collapse. Versus most people and the owners want this, right? So if you push your structure in the lateral direction, you like to have your structure operational and very limited damage, so that they can go in there, maybe fix a little bit and then stay there. But they don't understand, or we don't communicate that our goal or target is to prevent the collapse. Now, you may be asking, well, is that fair to the owner or whoever is managing that structure? Well, we can always do better than what the codes or the law says. Law says you cannot kill anyone. So if somebody wants a better performance, we can also do this, but somebody has to pay for it. So this is much more expensive. We have to make it elastic and stronger. So this is called performance-based design. It is slowly getting into picture, and this is only required in few locations. In Los Angeles, for example, for high-rise buildings, you are required to do this performance-based design, but for the rest of the world, we are trying to prevent the collapse of the structures. So what we do is, in typical design-level earthquakes, we like to make sure our typical ordinary structures will be life-safe. This is our target. Because of the example that I showed you, that the Japanese building, in Japan, they like to have fully functional buildings right after the earthquake, because they have so many frequent earthquakes, they can't just keep repairing those buildings. It will be too expensive. So again, if somebody wants to do it in Jordan or US or anywhere else, we can still do this, but this is expensive. So that's the reason if you go to Japan, and if you look at this column right in the corner, if it is, let's say, 1 meter by 1 meter, if you go to Japan and look at the same column, it will be 2 meters by 2 meters, because they like to stay in this region, because they cannot tolerate the damage that the rest of the world does. So when we look at seismic design, one of the major tools that we have is concrete walls or shield walls. So they save the building. they save the structure. So whenever it is possible in two directions, we like to put shear walls. This building literally collapsed for practical purposes. As you can see, the column here lost its capacity. The only reason it is standing and people were able to get out of this building is the shear wall here, and then there were a couple shear walls on the other side, and we have way too many examples showing the effectiveness of shear walls. That's correct as long as your floor plan is symmetrical. So these are 4 shear walls, and then there are all kinds of columns in this building. This building collapsed in about 10 years ago or so, and this is the core where the shear walls are located. Since it is unsymmetrical, that creates the huge torsional force on the entire structure, and that's how you see the slab. So I'd like to show some of these critical items. Another item is if we have these rigid walls, we like to continue all the way to the floor level. Otherwise, we will see these soft or weak stories. So this is another example from the US, from 1979 earthquake. They have these huge shear walls, and we like to keep the first floor level for garages and open, and suddenly during the earthquake, when you pull and push, you have huge demand, and when you look at the resulting forces, you have huge axial forces, and then those columns, this column here and the other columns all failed, and this building was almost on the verge of collapse. So I happened to look around in Jordan, and you can recognize, right? So, I mean, we can't blame people. This is what everybody does all around the world. You see there are cars here, and there are more here. I could see more, but I found this nice picture. There's nothing wrong with this under gravity loading. There's nothing wrong under lateral loading as well, but one needs to be very, very careful. So if you are the designer, these columns are carrying the entire load of the structure. And what we typically do is we design these columns and we extend it maybe 2-3 stories because we don't want to just keep changing the design. So if you have a design condition like this one, these columns must be much, much stronger than the upper floors. That's absolutely necessary. There are huge penalties in seismic zones in the US. So obviously we don't know what the designer did here, but someone needs to pay extra attention to these columns because upper floors are much more rigid and heavier than the lower floors, and the demand is the largest there. And like everywhere else, that's what we do. Well, what happens if we don't do that? So this is an example from Taiwan. They also have all these stores, and then in upper floors, they have the infill walls. This is the picture that I took from Turkey, and this is a small building, and it's almost collapsing. There's a permanent drift in the first story structure. Again, this is floor areas story, and there are no infill walls because they have glass and all the floor, and upper floors have these more rigid walls, and it's almost collapsing. So again, these requirements are all in the code, but we have to pay extra attention. These two buildings are from Osaka University campus that I was there for a while. Walking around, they are relatively close to each other, and I took these pictures, and I was giving a seminar. I showed these two buildings to faculty members and students. I said, there is something wrong with one of these buildings. What do you think? And so maybe I can, well, before I get to the conclusion, in one building, both of them are engineering buildings on the campus. In one building, this concrete block is separated from the column. There's a clear separation of 30 centimeters or something like that. In the other one, that concrete portion is rigidly or monotonically connected to columns. So in my mind, one of them is clearly and absolutely wrong and unacceptable. That's what I said, oh, there's something wrong here. And so in this building, although our column is running all the way down to here, we are not allowing the movement of the column. The actual column tends to be this much. Versus here, the column is moving. So that's what the engineer was thinking. So I asked, and I said, you know, this column, if somebody pushes to its limit, it is going to develop shear cracks and it's going to fail, versus this one will be able to move back and forth. So no one said anything, and I said, this is what I'm thinking. I don't know why this happened. And their culture is a little bit, at the end of the presentation, one of the professors came and said, you know, both of these designs are very good and acceptable and nice in Japan. He said, you know, this is standard design, that's what we expect and we do, but he said, this is also acceptable because when you do this design, you are wasting all this concrete material. By the way, in Japan, they don't use masonry blocks or stone or bricks. All the walls are concrete. And he said that when you do this, this is all wasted concrete. Here, that concrete is helping you in the lateral direction, providing extra stiffness. He said, whoever designed these structures, assuming this structure will always stay elastic. You will see when I say there will be shear cracks, I'm assuming at some point this building is going to collapse if you just keep pushing. He said, no, this building is not going to get there because the designer made it so strong and elastic, you will not reach there, and then you are taking advantage of this elastic stiffness. So the question, my point was still valid where if you make it a short column, then this is what happens because you have a huge shear demand and limited capacity to develop plastic hinges. Again, this is from Los Angeles area from 1994. We have, again, a lot of examples of these short columns. So I would like to go over this very, very quickly. When we do the seismic, when we do shear design, wherever you go around the world, you calculate your shear forces from structural analysis, lateral forces, gravity loads, and then you compare that with the capacity. You may be using different terms, but the system is the same. You do structural analysis, calculate the demand, compare with the capacity. But if you do standard gravity load design, you don't check this condition where you don't check if the columns are going to develop their plastic or flexural capacity. That's not the standard practice because we assume these non-seismic or gravity load design structures are not going into that region, and we will probably don't need to reach that flexural capacity. But under seismic loads or under very large lateral forces, we also need to make sure the capacity is larger than the lateral force to develop the plastic or moment capacity at the end of the column, and it is calculated from this equation. So what happens if we don't do that? So if we don't check that, and if we expose our structure to lateral forces, this is a very typical shear loading or shear failure with diagonal or almost 45-degree angles. And that's what we expect to have because we don't have the abilities to reach the capacity. So that brings up the question of how do we achieve that shear resistance? How do we prevent this type of failure? See, if you look at the spacing of the ties, they are maybe at 30 centimeters or 25 centimeters. Most likely they have these 90-degree hooks. They just open, I was showing you earlier, versus this is what we want in an earthquake. So we like to be able to have deformation. It's a huge deformation. If you look at the height of the column, let's say if it is 2.5 to maybe 3 meters, this is almost half a meter. That's a lot of deformation because this is a ductile column. Versus this one is experienced shear failure. These are shear failures. So now you can see the importance of this lateral reinforcement, transverse reinforcement, or column ties. So that brings up the issue of or concept of confinement. So if you are going to get something out of this presentation at all, the only thing that you can take out of this entire discussion is probably confinement and the amount of steel reinforcement. So in my classes at school, I bring a plastic bag, and it's just a plastic bag, and I ask students, do you see anything here when I crush it? There is no compressive resistance. It is maybe 5-inch or 5 centimeter diameter plastic bag. And then I have a cup of sand. And I ask them, does sand have any strength at all? Sand just flows, right? It has no strength. And then that plastic bag doesn't have any compressive strength either. So I asked one of the students to come and fill that plastic bag with the sand. So now imagine a plastic bag filled with sand. When you press on it, it takes a lot of load. It doesn't fail. Can you imagine the scenario that I'm talking about? And I asked the question, where does that strength come from? Well, the answer is confinement. So if you have a stack of if you have a sack and if you put some material in it like sand or cement, and if you push on it, it will carry a lot of load because the sack or the plastic is going to confine it. See, the plastic itself doesn't have any compressive strength. Sand or flour or whatever you are putting in there doesn't have any strength either. The column strength comes from that confinement. So we use exactly the same concept for our design. So if you put a lot of transverse steel in your column, then you are confining your concrete. So if you look at the stress-strain behavior of concrete, your unconfined concrete, if you test a cylinder, this is what you get. You apply the load, and then suddenly concrete fails, and this is your response. Okay, it is more like this one. So if you put one steel here, another one at 30 centimeter, another one, so you will be losing a lot of concrete, and you don't have too much confinement. But if you put a lot of confinement around your concrete, or if you put your concrete inside a steel form, and if you push on that concrete will be very, very strong. And that's a reality. So if your original concrete strength is, let's say, 20 megapascal, you will end up getting 35, 40 megapascals. It is exactly the same concrete. All you are doing is confining it so that it cannot expand. So this is exactly the same concept. Not only you are increasing the strength from here to here, you are also increasing the deformation capacity. Okay, so in a column, if you put a lot of steel or spiral around your column, you are increasing the displacement capacity as well as the strength. Again, this is exactly the same concrete in terms of mixed design and material. The only thing we are doing is we are confining and increasing the capacity. Since we know that in high seismic regions, we are required to put tons of transverse steel so that we can increase the strength, we can increase the lateral or axial deformation capacity. That's exactly what we do. In low seismic or non-seismic regions, we put much less steel. It's okay under gravity load. So going back to the column behavior, we have three possibilities. If you confine your concrete, then you will have this nice lateral force displacement curve, and it will just keep taking all kinds of nonlinear loads, and this is exactly what we want. And if you don't have enough shear reinforcement or capacity, if you pull and push, it will fail in a brittle manner, boom. And most of the building columns, unfortunately, fall in between. You get a little bit of flexural capacity, but right after you reach that flexural capacity, you will see the shear failure, and then you will see the column failure. Most of my research over the last 20 years or so has been on these type of columns and how do you model them. Unfortunately, these shear cracks and shear behavior is not included in the current structural analysis software for a good reason, because if you are designing a column like this, you are not expecting lateral loads and you don't expect these type of shear failure. That's the reason they are not in there. But if you are assessing an existing structure for retrofit, we need to understand this. So this is what my research is about. But if you have this well-designed flexural columns, then we have all these options. We can make it very simple, plastic hinge model in the nonlinear range. We can have fiber models. We can go all the way up to finite elements. But please be mindful that spending a lot of time and developing this finite elements models doesn't mean that this model is better than this. So whether you do this or this, you have a lot of assumptions. Okay, so again, making this very complicated model doesn't mean that it is going to give you a better response. So I am almost done with this column-related research or discussion. The reason that we need to assess and check these shear critical or non-ductile columns is we may need to retrofit them, especially the existing structures. At least in the US, we have 3 code guidelines that we have to go back and check the capacity of these non-seismic or low seismic columns like this one. So in terms of research and unknowns, we still don't know when this shear failure happens, this point C. So this is coming from the code, and the code says if you want to assess the existing capacity or retrofit your structure. Then it says in a computer program, you have to model your columns or joints or other components using a model like this one. Again, they provide some guidance, but still the C and D, which is the shear failure location, is still not clear. And not only that, the failure point E, which is right here, is not very clear either. So that's the research that I was thinking about getting into details, but I decided not to, just to keep it general. If you are interested, I have a lot of publications and research in that area. So I am in an area, I did my PhD and earlier work in seismic work. Now I'm in an area where we don't see too much earthquakes, or it's a low seismic region, so there's less interest in seismic. And there was a quick switch for me from seismic loads to progressive collapse that I will talk about in a few seconds. As I said at the beginning, again, I took these pictures from a building in 1999. This building literally lost these two columns. If you look at here, you can push your hand in there. So this column is completely gone, the other column is completely gone, and still the building is standing. Versus we have examples, if you lose a single column, the building collapses. So we still try to understand this question. Now, when we look at all other aspects of loading, we may have scenarios where your building may be subjected to fire, impact, blast, all kinds of other loads. So the general procedure for those type of questions and check the collapse assessment is called non-threat loading. So we ignore the load effect and say, and check if our building is going to collapse or not. So the question is, if you lose a single column from this building from here or here, is this building going to collapse or not? So that's the problem, and it's called progressive collapse. So again, there are examples. These are non-seismic collapses where somebody or somehow lost the column here and then part of the building collapsed. And this is a collapse from Korea. They lost a couple buildings and collapsed. And we have too many examples of that. Again, when we do our research, we are assuming we are going to lose one column, and then we are trying to see what happens to the rest of the structure and how the loads are distributed. So this, we ended up testing 10 buildings, mostly on our campus. It's a relatively large campus, so they always demolish some buildings and put new buildings. So this was one building that was demolished about 5 years ago or so. And what we did was we worked with the demolition company, and we removed this column physically. And we instrumented the rest of the structure. So if you look at the sides of these columns here, we put the strain gauges, and also we have the displacement sensors right here. So, and then the construction company ended up cutting this column for us. So initially this column is carrying certain load, right? So as soon as you cut it, that load has to go to the other locations. So we also did a lot of numerical simulations, and at the end of testing all these buildings, we found out that if you have, let's say, 100 kilonewtons here, roughly 30 to 40 goes to the next columns, and then maybe 30%, 20% goes inside the building. Again, this is the floor plan for that building, and this is the column that we removed, and then we have all these instruments located at different locations, and we could also see the deflection of the beam, and then we could see when we remove this column, we could see exactly how much load is transferred to the neighboring columns, so that students could do a lot of analysis and see what that means. So this is the 2D model of the original structure. This is where the column is located, and as soon as you remove the column, there's a huge moment demand on the beams right above that. Again, just to keep it shorter, we have a lot of publications on these issues. I just wanted to show you what results we got. So these dashed lines are the actual measurements that we got out of strain gauges. And then we have the nonlinear dynamic analysis and static analysis. We were trying to match and see what happens to our structure versus what we are getting out of our nonlinear or static analysis. So now going back to the practice, in the US, if you are designing any government structure or military structure, at least you are at this point required to show the authorities that your building is not going to collapse after you follow this UFC or GSA guidelines or code standards. So what these guidelines are telling you is if you have a building like this one, you are supposed to remove one column from the perimeter or corner column or at different locations inside the building and analyze the building and show that or demonstrate that your building is not going to collapse. Again, this is your progressive collapse guideline. So when you do these analyses, you are assuming this column will be gone for some reason. We don't know and we don't want to know, because if we say it is because of blast or fire or impact, then we have to be specific about the blast or pressure. Here we are not interested in the load, rather we are interested in what happens to the structure after that. Again, we kept doing our research. Out of the 10 buildings that we tested, I'd like to show you the next one. I'll show you only maybe two. This was another building on campus. This is a steel building. First, we cleared the infill walls in the first story right here, and we removed those columns first by torching the steel columns, and then if you look at it, we torched them all the way to the edge. There was a little bit of steel, and then we had we cut a hole here, and then we just pulled the column, and this is how the column is removed. So we removed 4 columns one by one. As you can see here, the building is still standing, and these 4 columns are now gone. So again, during this process, we were able to measure and monitor the response of the entire structure, including the columns. Obviously, then we did numerical simulations. We removed these 4 columns from a 2D model and a 3D model. And then one approach that these progressive collapse standards or codes are asking us to do is static analysis. It's very simple, although it is conservative. It says calculate the maximum demand that comes from the structural analysis after you remove your column, and compare with the maximum capacity of the members for the beams and columns. And again, this is relatively simple compared to dynamic analysis. When we did that for our building, we found out that at several locations, the demand on the columns were quite huge or quite large, and at least at 4, 5, 6 points, we exceeded the limit that code was telling us. So according to the code or standard, it is conservative, obviously. Our building was supposed to collapse, but in reality it didn't, because in reality we do have a little bit more reserve capacity. Our structures are good news that more robust than what we designed for. Again, see, when you do the static analysis, it is quite conservative. It is simple. Our measured response was way up here, but when we did the static and dynamic analysis, we were always conservative, and then we were getting much larger displacements. So the last building that I'd like to show you is a masonry building, and this building did not have any concrete columns, and all the loads were carried by these load-bearing walls. And in this building, we ended up removing 4 walls, and then we did the same analysis, and we checked the progressive collapse guidelines, and then we ended up evaluating them. So I'd like to summarize what I talked about today, maybe move a little bit faster, but although I focused on seismic design, if we do everything for seismic design, effectively we are doing a good job with progressive collapse as well. So I'd like to repeat the same conclusions with different columns. So again, as a final note, I'd like to repeat that we like to put as much transfer steel or column ties in columns as possible, so that it will make our members stronger, as well as more ductile and deformation. We will have more deformation capacity. I think I already talked about the other items. And this is the end of my presentation. Thank you.
and will have a direct impact on our building costs right now in Jordan, especially during the last collapses here in Jordan. Now, I think we have a room for 3 or 4 questions, the maximum, before the second speech will be happening. So, please, identify yourself, please.
Myself, I am Amun Atul. This is a great presentation.
Thank you.
Thank you very much. I just have one question. We all engineers, once we look at these pictures, we do understand the main reason for the collapse. If others look at these pictures, they're not engineers. The common reason for collapse can be explained to them. Is it a lack of the experience of the workforce, a lack of designers, the cost of the design, they're not seeing the cost of the design. So how we can convince the clients to either engage that quantitative scheme, okay, to prevent this kind of collapse, or to stick to the codes where the collapse will be prevented. So
You know, that's an excellent question that has been happening in California for the last 10 years or so. That's the reason this performance-based design came up. So in your question, insurance companies are also involved. So the question becomes, you go to the owner and be honest and transparent and say, I'm designing this structure, you have to pay me $2 million. According to code, I can't go below that so that your structure will be safe after an earthquake. But then you will say, well, you may need to shut down your building for 1 year, or you may need to demolish it after a major earthquake. Be aware of that. Suddenly, the client or the owner says, oh, is there another option? Then you say, well, if you pay $10 million, after a major earthquake, you will go in there and you will work in that building as if nothing happened, right? You have to pay for it. And then you can also give in between. That's exactly what the performance-based design, performance objectives and outcomes are designed. So, and insurance companies, they also say, okay, if you go with that option, we will reduce your insurance premium. So this is exactly the discussion. It is the money, right? So now the owner needs to make a decision. If that building is going to be there for the next 50 years, and the likelihood of an earthquake is quite high, so are you going to take the risk and shut down your building for 6 months, or are you going to pay more upfront? That's exactly the question.
the relationship, the direct relationship between the cost and the quantity and the quality. So this might lead us to think outside the box.
That's exactly right.
Some alternative.
That's exactly right. But one problem with this performance-based design is, with collapse, we are very good. We know the maximum capacity, but when it comes to intermediate performance levels, it is a little bit difficult to quantify. So that's the reason this interaction is absolutely necessary. You will tell the owner, if you pay this much, this is how much steel I'm going to put, this is how you are going to benefit from it. Then it is not our decision, right? It is the owner. Yeah.
Thank you. Engineer Habib, please.
Thank you for this very interesting lecture. My question is simple. Do we have any special details when we are designing for missing column for, let's say, a blast or explosion, rather than these we do in earthquake details and so on, especially for the joints?
Yes, I suggest these are both free documents. GSA is a government code for buildings in the US. So if a city or government is putting a building, they have to follow that. And then UFC is the military code. So if the military has a building, they have to follow this. These are free. If you go to Google and check them out, and you can download. And this is the alternate path method. I had a lot of slides that because of time limitation I didn't put there. They ask you to, part of this is also in ACI 318, so you have to have ties, especially for precast structures. So this is a major problem for precast structures. I'm not sure if you have too many precast concrete structures in Jordan. So I will say those are the two that works. Again, these codes are intentionally not talking about the load. It can be fire, impact, blast. They say, tell us or show us that your building is not going to collapse if you lose these columns. And your building becomes very robust. As I said, interestingly, if you do high seismic design for high seismic regions, then you automatically meet most of these criteria.
We have room for one last question.
Thank you.
The lady there.
Wow, that's an excellent question. I was a graduate student in 1999. Two earthquakes happened. The one in August was a major one. And then there was another one in October. It was only 40, 50 kilometers away. So I've seen a building, I never forget about it. They had short columns, and when I talked to the owners, after the first major earthquake, they had these diagonal cracks in their columns. An engineer came in and they said, oh, these cracks are minor. Maybe they were right because it was such an earthquake. They said, you will never see another major earthquake like that one. But in the second earthquake, that building collapsed. I could still see those columns in there. One of the owners they had a bunch of apartments, she said, an engineer came here and said, oh, it's okay. And we were in the building, and after the second earthquake, a big portion of the building collapsed. So going back to your question, anytime you see diagonal cracks in the walls or beams or columns, that's an indication of shear failure. It may be, if there's no earthquake, it can be ground settlement or some other reasons, but diagonal crack means shear, and that's extremely dangerous. That means if something happens, it will be brittle. Versus because of flexure, you will see cracks, maybe vertical or horizontal, in the tension regions. So it is a little bit better compared to shear, but the diagonal cracks are extremely dangerous anywhere you see them, and you better fix them if they happen. So that's what I will say with concrete structures.
Thank you.
Oh, okay.
If we have time limitation, we couldn't have any more questions.
Very important question. Short columns. Can we resist the problems of with respect to short columns? It is famous here in Jordan, especially in basement and in school buildings. They connect the walls with the columns. Can we resist? Can we solve this problem by increasing the shear force for the short columns or not? Thank you.
That's an excellent question. Thank you for asking, although we have very short time. They are very dangerous. I can show you many examples from Italy, Taiwan, Turkey. I've been to several locations. Those short columns, if they are less than 1 meter less, they must be fixed. Either they have to fill those windows or they have to clean those areas or put some kind of separation. So if your columns are short, it is very difficult to resist those lateral shear forces. It is very difficult. So maybe we can look at the situation, but it's a good idea to get rid of those short columns if there is earthquake possibility. Sorry. Thank you for your patience.
I would like on behalf of the organizers and myself to thank Dr. Sezen for this excellent presentation, and I would like to introduce the second keynote speech right now. Okay. As you know, the world's population depends on an extensive infrastructure system which includes roads, sewers, highways, buildings. The infrastructure has suffered in Jordan and all parts of the world in the past years from neglect, deterioration, and lack of funding, which lead to global infrastructure crisis. Our second speech or keynote speech will be dedicated to the subject of infrastructure health monitoring opportunities and challenge. This will be delivered by Dr. Khaled Al-Shibli from the States. And allow me to introduce Dr. Al-Shibli. He is a professor in the civil engineering and is currently serving as the associate department head, professor and coordinator of geotechnical and material group at the Department of Civil and Environmental Engineering at the University of Tennessee, Knoxville, Rtk, United States of America. He served as a faculty member at Louisiana State University for almost 11 years before joining Rtk in 2011. Professor Al-Shibli earned his BS and master degrees from the Jordan University of Science and Technology in 1988 and 1991 respectively. Then he earned his PhD in geotechnical engineering from the University of Colorado at Boulder in 1995. He worked as a project scientist at NASA Marshall Space Flight Center between 1995 and 2001. Professor Shibli was the recipient of King Hussein of Jordan First Class Honors Awards for BS degree in 1988 and master degree in 1991. In addition, he is a recipient of many awards, including the NASA Group Achievement Award in 2003, Engineering Faculty Professionalism Award from Louisiana Engineering Foundation in 2005, and American Society of Civil Engineers 2018's James R. Cross Medal. I would like to invite Dr. Al-Shibli to deliver his speech. You have, Dr. Shibli, 45 minutes to finish.
شايف الماوس can help الماوس I see it here, I don't see it here. Here it is. My presentation. هذا البرزنتيشن تبعي. هذا هو. كان مفتوح. لا بس شغله. حط لي على السلايد الأول. السلام عليكم ورحمة الله وبركاته. أول شيء حاب أشكركم على استضافتي يعني دعوتي لهذا المؤتمر. شرف عظيم إلي أني آجي لهذا المؤتمر. أنا انولدت في سوريا وبعدين طلعت عشت في السعودية، وكان من حسن حظي أني آجي أدرس في الأردن. الآن قضيت تقريبا 32 سنة في أمريكا، بس طلع على حياتي أفضل أيام حياتي كانت أيام ما قضيتها في الأردن. فأشكر الأردن يعني حكومة وشعبا على الجميل والدراسة والخبرة اللي اكتسبتها. صحيح يعني لما طلعت لأمريكا كان تأسيسي في الأردن ممتاز، وكان من حسن حظي، وكل ما وصلت إليه بفضل الله تعالى أولا، ثم بفضل جهود أساتذتي في الأردن. فشكرا للأردن والأساتذتي في الأردن، وبارك الله فيكم. فراح I switch for English يعني respect ل some of non-Arabic speakers. طبعا انتم غلطتوا في العنوان لما سألتوني أتكلم على infrastructure monitoring. في هنا زميلي وصديقي العزيز الدكتور جمال نصيرات. He's a practicing engineer, he works in the field. I'll do my best, but for any difficult questions, Jamal is here to help. My presentation is two components. The first component, the title of this topic, infrastructure health monitoring. I will start by a basic definition of it. I'll give you one example of it. Then I will switch my presentation to a kind of a new development, the use of drones in civil engineering, then I will be very frank with you about highlighting some of the challenges that encounter us. And I'll be very frank with you, and might be offensive for some people, so please accept that from me. It's a kind of some thoughts I have, and I'm glad to see some of the young engineers here. I think the young engineers are the future of our profession, and maybe it's time for us really to pass the torch, يعني الراية إلهم, to carry it to the next level. And then I will just show a couple of examples about what's next, where are we going as a profession and as a development, and with some concluding remarks. So the infrastructure health monitoring, it's a kind of recent years. We have some of the civil engineering structures are aging. It's very costly to replace them. So we are using all of these kind of instruments. So just to go with some basic definitions, it's basically the concept refers to an implementation of methods to evaluate the conditions of a structure based on a combination of observation, measurements, analysis, and modeling. Other definitions, it's basically the objective of this concept is to give at every moment during the life of a structure a diagnosis of the state or the condition of the constituent materials of the different parts and the full assembly of the whole structure. It's also, it consists of determining measurements, location, and severity of the damage. Another kind of component or issue to mention here, it has a continuous operation of the instrumentation of the structure health monitoring can be used to implement visual inspection of the bridge and possible detection of damages. It's also very necessary for systems that have a major adverse impact in case of a failure. For example, we have a lot of dams in different countries, very expensive to replace, but you might worry about liability issues or safety issues. So these instrumentations can give you critical measurements to safeguard against any failure of these structures. And it's also in a country like the United States run by lawyers, it can defend you against lawsuits. Really lawyers are, the world is much better without lawyers, but they are running the show in the United States. And nowadays, sensors are becoming more affordable financially. So it used to be very expensive. Nowadays, they are very affordable, so they can be a good tool. So the cost of the health monitoring structure, that is there are so many components feeds into it. Of course, the size and the type of your structure, how many sensors you want to include. Are you doing static or dynamic measurements? Big cost difference in the data acquisition component. So the site accessibility, how easy to access the site, install the instruments. Wired or wireless sensors. Big difference because most of the sensors nowadays are wired, so you need to be very careful in running the wires all the way to the data loggers to get that. Are they isolated individual sensors or they are connected to each other? Are you going to do manual collection of the data where the data is saved locally? You have to go physically there, plug a SIM card to pull the data, or they get transmitted to your office? What are the environmental and vandalism conditions? You have to safeguard them against vandals, which is a big problem, really. How you transmit the data. The ideal way is to transmit the data to your office. And it's also you build in the software a warning system, even if you are sleeping at your bed and something goes abnormal, you get a text message to warn you that something is going on. You need to be aware of that. And of course, the real-time store data, it produces a lot of data. How do you handle the data? How do you separate a kind of noise from a real data and how to retrieve it? So this is the big picture of it, where you have whatever you are monitoring, whether you are monitoring a damage or a structure itself. So then you defined what are the physical phenomena that you are trying to monitor here, and you look here into a kind of diagnosis or a health monitoring component of it. The sensors, of course, detect different phenomena here, and you pass it to the data monitoring, and of course there is another one is a kind of health and usage monitoring. Of course, you accumulate a lot of data, and you integrate it into your management system. So it's a very broad concept. So here is, I'm a geotechnical guy, you know, I'm saying I'm a foundation guy. We are like, foundation engineer is the dedicated engineer. You cannot brag about your work. You cannot tell people I designed the best foundation, because people judge by seeing things, right? So I tell my student, foundation engineer is the mother, like the mother in the house. You cannot have a house without the mother, right? So, but at the same time, you are only famous in the negative way. If there is a failure, everybody will say that's a bad foundation engineer. If everything is good, nobody will be saying he's a good foundation engineer, right? So here is an example where if we have a retaining wall, I'm borrowing this from Professor Titi here, you have these instruments in the field, you have the data logger, you have to run these instruments into a data logger to save your data. Now you have to transfer your data to a server where you store your data. You can transfer it nowadays through the wireless system, signal phone, signals on the cellular network, and you save it on the server, and from the server here, you transfer it to an office computer or even on your laptop or iPad, and you look at the data even on your phone to make the judgment on that. So this is the map of the United States. The project I'm going to talk to you is in Louisiana. I was at Louisiana State University, so this what happened in a very small island here. The first example I'm showing here. Currently, I'm in Knoxville, Tennessee. This is the state of Tennessee. I think all of you know where is Atlanta. We are 3 hours north of Atlanta. We are east of Tennessee. The island is very small. This is the famous city of New Orleans, the lake north of New Orleans. So this is a very small island called the Grand Isle. This is Khalid al-Mexique, Gulf of Mexico. طبعا the Mississippi River, نهر المسيسيبي, before it goes into the Gulf, it develops what we call it wetland, مستنقعات Louisiana, with marshes here. So this island is a very small island, the south tip of Louisiana, called the Grand Isle. You know, here I'm zooming to see it. So you see this is Grand Isle. Another zoom there is one bridge that crosses the mainland to Grand Isle. So without this bridge, this island is totally isolated. Then Hurricane Katrina came, and I was in Louisiana when that hurricane came in 2005. And Hurricane Katrina caused the highest damage of a natural disaster in the US history. It flooded New Orleans, and actually it challenged the Louisiana DOT to change their design of the bridges. Before Katrina, bridges used to sit by gravity. They are not anchored to the foundation. The hurricane, the waves of the hurricane picked the bridges, lifted them, and put them in the water. So now Louisiana designed the bridges. They anchored the superstructure to the foundation because of Katrina. So this is the bridge you see. It got picked from the foundation, thrown in the water. This is the island, you see it here, and totally isolated the island. So the Louisiana DOT, after the hurricane, they picked the deck of the bridge, they put it just to give access, and they decided to build a new bridge, and that's what I'm talking to you about. So we instrumented that bridge, and the objective was to monitor the performance of, this is what's called integral abutment bridge. So some of you are not familiar with it. We instrumented 2 bridges, but because of the time limitation, I'm just talking about the Caminada Bay Bridge. So the integral abutment bridge is the bridge where you connect the foundation to the superstructure. It's like, for structural engineers, like a framed structure. So this is the deck of the bridge. You connect it. This is the foundation, what we call it, the bent here. So you connect it. The advantage of that, you eliminate the joints on the deck of the bridge. And that there are what called semi-integral abutment bridge, where you connect it on one side and you leave the other side free to move, or full integral abutment bridge, you connect it to both sides. What are the advantages of it? You don't have joints on the deck of the bridge, which is very nice. There is no maintenance for these joints, and you will not hear the pumps as you drive there because of the joints, no settlement. And it has a huge cost saving with the initial cost and over the life cycle of the bridge. With these integral abutment bridges, the highest percentage of stresses are the thermal stresses. When you are heating, the bridge will expand, and when it's cold, the bridge will be contracting. So these are the thermal stresses you need to account for. And also that will be, of course, you are connecting the bridge to the abutment and the supporting pile, so you need to be very careful in designing it. And also with the approach and the sleeper slab as you approach the bridge, and with the granule fill materials. So the instrumentation plan, this is the, probably you do not see a lot of details, but this is what we call it bent one. So you approach the bridge here, you have a fill material. Here is the approach slab. And then bent two, you have about 300 feet continuous unit. So this is one unit of the bridge. Then you have a joint, another unit, and so on. So the focus of my work was on bent one here at the beginning of the bridge with the fill material to monitor the piles and the behavior of that bent. And it's connected to the bridge, so it will be a rigid connection here. So here is a closed schematic. You have the bent here, and we have 4 concrete piles. And I will give you the details of the piles in a minute. And we instrumented 2 of the piles here with strain gauges. And here we have what we call them pressure cells and displacement sensors. So I'll give you details of those here. So there are a huge collection of sensors. So the sensors here, I'm just giving you a few of the sensors we used in our work. So this is thermistors, which is basically temperature sensors, just to give you a temperature, which is very important, to measure the thermal stresses. And they are pre-packaged there. They are very cheap, connected to wires, and you just install them wherever you want to install them. You can cast them in the concrete, or you bury them in the soil. These are what we call them sister bar strain gauges. So it's a very small strain gauge pre-packaged here, but they sell it to you with a rebar. The rebar is about this length. And what you do, you tie this rebar to your reinforcement, and you run the wire. So this is very effective. You tie it to the rebars to measure the strains within the concrete. In Louisiana, there are different piles for different kind of conditions. The pre-stressed concrete pile is one of the favorite piles, driven piles. As you know, there are drilled shafts and driven piles. So here I'm talking about driven piles where you precast the pile, you bring it to the field, and you hammer it in the ground. So the piles we use, they are huge piles. They are 3 feet by 3 feet square pre-stressed piles. So they cast them in a pre-stressed plant. And you see, these are 64 feet long piles, and they are hollow on the inside to save on the concrete, except when you reach the bottom of the pile, they make it solid and they increase the reinforcement to enable a kind of taking the stresses during the driving. So we tied these sister bar strain gauges to the pre-stressing strands in the cast plant, and they pre-stress the strands and they lock them in the pile. So all of these piles are pre-stressed compression piles. I'm showing here the plan view of the bent. If you look at it from the top, it's carried on 4 square piles. So we instrumented 2 piles, one edge pile and the one next to it. This is the pile driving process. So this is what we call it steel template. And these are, you see the 4 concrete piles, and you see the hammer here is driving the first pile. And of course, when we install these strain gauges, we have them into PVC pipes a little bit below the surface to survive the driving. So here is the details of the bent itself. So this is a cast in place bent. And here are the 4 piles. This is the engineering drawing. So here is the you see the white PVC pipes. That's where we cut we chip the concrete on the surface. We fished. We run the wires. With the field instrumentation, the most difficult job is really to take care of the wires and make sure you don't damage them in the process. So here, after they drove the piles, we went there and we connected these PVC pipes to run to run the wires and route them to the exit side to the data acquisition system. You see here is the top of the pile. You notice here, this is a reinforcement. This is what I told you about, is to tie the pile to the superstructure. So what they did, they drilled holes at the top of the pile and they epoxied these 3 bars, and they are connecting them now to the bent, and then the bent will be connected to the superstructure. The pressure cells, you know, all of us studied, you know, the lateral earth pressure, Rankine active pressure, and passive pressure. So these soil pressure cells, they are very good in measuring the pressure anytime you want to measure the pressure. So you buy them like this. They have like a circular in shape, and they are connected to their data acquisition. And the way you install them, so we install them on the face of the bent. So this is the approach slab, the fill. And when basically the bent moves against the soil, they measure the pressure interaction between the bent and the soil. The way you install them, you know, this is the face of the bent cast in place, but still, you know, the concrete surface is a little bit rough, so you want to establish a very good contact between the sill and the surface contacting. So it's very easy. You just mix a kind of sand with a mortar there, and you just create a surface, and you push the sill, and you bolt it with bolts, and they worked fine. So here you see them. We installed 9 of them. So this is the face of the bent. This will be filled as an approach slab, fill material and approach slab. So now as the bent pushes against the soil, they will be measuring the pressure. This is called vibrating wire tilt meter. The tilt meter measures the rotation. So when the bent rotates, it gives you the rotation angle. It's very easy to install. You see it has a bolt there, so you just drill a hole. So you drill a hole in the face of the bent. You tie the bolt, but you need to create a space around it. You don't fill the soil around it. So what you do, you have a cover aluminum plate, and then you fill the soil around it. This is called deformation meters or displacement meters. There are many kinds of them. So this kind has 2 flanges. You see a flange here and a flange here, and a rod between them. So the way those work, you don't want to create or to measure 1-point measurement. This will be measuring a deformation between the 2 flanges. So we have 2 sizes. We have 4 feet ones and 7 feet ones. So here's the 7 feet ones, where we bolt one end of it to the face of the bent, the other end in the soil. So this will give me a measurement over all of this distance. We have the 4 feet ones. We installed 2 kinds. One bolted to the bent to a distance with a little gap, one in the soil. So the one in the soil measures the deformation in the soil, and the other one will be measuring relative displacement between the bent and the soil. So this is a brief overview of these measurements. I don't have time to talk about all of the details, but I'm just showing you a few examples here. So this is the pressure cells, and I'm just showing you 2 times at the winter time. This is January 4th to 8th. Louisiana is very warm. I'm sorry, I'm using here degree Fahrenheit, not degree C. And showing you here the temperature that ranges from somewhere in the 50s to the upper 60s, 70s. So there's a variation in the temperature. So you see here the different pressure cells give me very low pressure, some of them positive and some of them negatives. How do you get negative pressure? This is basically a cold season, so the bent is moving away from the soil. So it goes to 0 or below 0, a negative value. It's almost no contact between the soil. But the measurements are very small. You know, here is a kind of less than 1 psi there. Then you go to July, a hot season for Louisiana, where the temperature is very high, and most of them shift to a positive, but the highest one is about 3.2 psi. And if you convert it to a classical soil mechanics pressure, that is a reasonable value for that. So these sensors are detecting the bridge movement to and from the soil. Here I'm showing you the displacement. How much is the bent is displacing, pushing and pulling using these displacement sensors. Again, I'm just showing you brief measurements. So this is the cold season, January. Very, very small displacements. You are talking about less than 0.1 inches displacement. Mostly is 0.05 inches displacement. You go to July, the hot season, it moves in the other direction. The bridge is pushing against it, but your displacements are very small. This is for the piles now. You instrument the pile, so you push on the pile and you pull on the pile itself for structural engineers here. So we have the 4 levels of these strain gauges. So I'm plotting for you from January to then we go to October, the fall season, the spring season, and the green is the summer season. So clearly the pile is bending and changing. But look at the stresses. These are the bending moments in the pile. And notice here the units are in kips, inches. And if you calculate, I'm showing you here the moment in the x direction. So the x direction, this is the lateral direction. The traffic direction is the y direction. And if you calculate the theoretical cracking moment, 4,518 kips, inches, and the pile enjoying life, less than 300 kips, inches. If you go to here is the bending MY in that interior pile, again, you detect all of these thermal stresses, but again, the stresses are very small compared to capacity of the pile. Here is an exterior pile, this pile on the edge. Again, very similar behavior, very small stresses compared to the crack stresses. And here is the MY in the traffic direction for that pile to this one. So as a conclusion, you know, at the end of the project, I told the Louisiana DOT engineers, I'm sorry to tell you that, but your design is very conservative, and the pile is enjoying very low stresses there. And these piles probably will survive for a long time, and the design is very conservative. So that brings to the next part. You know, I see a lot of young engineers here, and maybe it will be worth talking about, you know, when we talk about field instrumentations and health monitoring of structures. In recent years, the drones became a kind of a very good tool in many civil engineering applications. And I looked at, tried to research it in Jordan, if the drones are allowed, and I checked الويب of هيئة تنظيم الطيران المدني الأردني. I couldn't find information, but when I did further search, I can collect from non-official website in Jordan that drones are allowed to be flown with some regulations, licensing, and stuff like that. So we invested in 2 drones. So basically the drones, it's called unmanned flying object, sometimes UFO, or unmanned aerial system, UAS, or UAVs. Of course, there are cheap drones where you can buy them for $200 to fly them with cameras, and they can serve good purpose, and there are a kind of research drones here. So we bought 2 drones, one DJI Matrix 210 RTK, and one larger one. And the difference between them is really how much weight they can carry and fly. So the first one can carry up to 5 pounds. The other one can carry up to 12 pounds. So I'll give you a general overview, and this might be a good project for some of the young engineers, or if you want to invest in that direction. I think that will be a good capability to add to the engineering market in Jordan. So you have to use, with the drones, you have to use the Rtk positioning. So this Rtk is a kind of an instrument. You have it in the ground, and this will be serving as a reference for the drone itself. Also, the drone has a GPS system on it, but it needs to have a kind of reference point. So when you use the Rtk system here, it's basically you bench the measurements of the drone to it, and it gives you more accurate coordinates, and it's also help the drones in case the drone get confused for whatever interference and stuff like that. The Rtk ensures the safety for that drone. So the Rtk is a very small instrument. You just take it to the field and you have it on the tripod sitting on the ground, and it will be communicating to the drone. So with RTK, your accuracy can be less than 1 inch. Now we are doing a lot of surveying work, and this is the common use of the drones. So for the surveying, if you want to do surveying, you will be buying those pads. So you will buy 6 of those pads. These are solar powered pads, and these are has GPS coordinates. So you take them to the field and you turn them on, and you just distribute them in different places in the field. And the idea here, when the drone flies, it shows the pictures of those pads. So when you analyze your data there, you know the physical location of the pads, and you know the GPS coordinates of the pads, and then you will have very accurate measurements of the elevations here. And actually, they give you an accuracy less than 0.5 an inch. And the good thing about these drones, you do most of your work at the office. You plan your trip, you download the maps, and you decide. For example, here we flew the drones to monitor a slope. So we decided, that okay, these red dots, it's basically where when the drone flies, it stops at that red dot and take the pictures and move to the next one and take pictures. So when you go to the field, you are charging your drone, stuff like that. It takes you about 20 minutes to unpack, launch the drones. With a kind of 30 seconds of flight, it generates data equivalent, if you send somebody to the field, will be working days to do that. Very quick flight, very accurate measurements. So here is an example of we flew it next to our engineering building. They are doing the foundation for a building now. It's up $130 million project. So you fly it over, you get these measurements. Now, the drone is just a vehicle to bring instruments. You can use it for a lot of applications. So I'm giving you an example here. If you are using the LiDAR, it's a kind of a 3D laser scanner. This is very accurate. If you want to map a 3-dimension map of a building, you fly it around the building. It creates for you a cloud, very accurate cloud. You go to your office and create the 3D map. Of course, the common cheap one will the photography, land surveying, inspection in case of disasters. Easy to do that. Environmental analysis, construction management, where you can monitor the site, safety analysis, agriculture, big thing in agriculture development. You can fly over areas, big areas. Acoustic emission sensors. Even nowadays, there are underwater drones. They go under the water and take images. So why we fly drones? They are very safe. They are very, very fast and very cost effective. Another good example of the drones, on our campus, the facility service, they have underground steam lines for the heating system. نظام التدفئة, pipes under the ground. Pipes, they are about 6 to 8 feet under the ground. And these pipes, they leak steam. And when they leak the steam will heat the soil to the surface. But they do not know where to dig. So they want to know where are the leaks to go to dig in these spots. So we help the facility surface. So we flew these with thermal camera. So it's a thermal camera. It has both an optical camera and a thermal camera. So you see this optical image, and you see the thermal image. So these are what we call them the volts. So the white means it's a hot spot. So we were able to pinpoint for them where are those, the leaks, and guide them. Now they go, where are the leaks? They go dig and do it. So that's really an amazing application. It's also in case of, in the United States, we have roofs that leak all time. You have rain leaks. So you want to know where are the leaks. And of course, the heating of the house will dissipate there. So if you fly over the roofs, you see these hot spots and repair them. In case of natural fires or floods, the drones will be really a big thing. So you can do them in search missions. And actually, when a disaster hits, the first thing you lose communication, the internet and the infrastructure, right? And the internet becomes very critical to operate. And actually, you can use the drones as internet hotspots. So you can fly the drones with these receivers, and they will establish for you the communication network. So we get a lot of disasters in the United States. يعني كل جزء من United States مبتلى بمصيبة معينة. احنا في تينيسي عندنا التورنيدوز. الhot wind when the season changes. So the tornadoes will be ripping through, you know, the middle of the state, makes major damage. So for the state agencies, actually, we have volunteers network where we can fly them in case of disaster and get that one. You can also nowadays, you can have these sensors, especially on the bridges, sitting passive. They are not powered. They are waiting for the power. And when you need to get data on them, what you can do, you can fly the drones, and on the drones, you can send powers to stations, and the stations will power those sensors, and then you collect the data and go. And that's very kind of appealing, especially when you are monitoring something close to the surface in there. So then sensors, they have what we call them roving hosts, and you fly the drones and wirelessly transmit the microwave energy to these sensor nodes. You activate those sensors, you do measurements, you collect the measurements and transmit them and get them back. So now I shared with you two examples, a classical field instrumentation example and the drone as a new technology. So I want to share with you some of my thoughts, and again, I hope you don't be offended by my thoughts. You know, I'm just here some, you know. I think our work as civil engineers, you know, impacts a public safety, which is a blessing and a curse at the same time. I mean, we are proud to serve, you know, our community, our countries at the same time. But at the same time, when I'm right, nobody cares. When I'm wrong, nobody will forget. And that put a huge responsibility on us as civil engineers, and we should be proudly to carry that. But our profession is very slow to adapt new technologies and new materials. And probably that's due to, you know, all of our design is driven by codes. And that's good and bad. You know, the codes usually, you know, I work in federal committees, Transportation Research Board, I work with the ASCE. So all in the United States, we have the federal and state agency government. They always have good intention, and the code is meant to be where you safeguard against malpractice. So you want to avoid the major collapses and stuff like that. And these design manuals, in my opinion, they create نظام بيروقراطي. النظام بيروقراطي, don't take it in a negative way. You know, these are agencies, they are not easy to change. And if you look at these professional agencies, you know, a change is a kind of very slow. So I'm just giving you an example. I'm critical of my profession. Here, you know, I took this picture 10 days ago of a highway. So this is an old way of paving those highways. It will not need maintenance for hundreds of years. The same road, you know, coming from this side, this is the same road. You look at the new way of doing pavement. So here's the old pavement, here's the new pavement. The new pavement is not doing well. So probably there is a good, you know, the pavement companies, maybe they want a pavement that fails all times to stay in business. You know, and I joke with my pavement engineering professors, I think you don't want to solve the problem with the pavement. Maybe that's why, otherwise you'll be out of business. Here is another example. This is my civil engineering building at my university. 25 million donation by one of our graduates. His name is John Tickle. We named the building after him. John Tickle, he makes fiberglass composite materials. So as a kind of appreciation for John Tickle, this is a bridge that comes from our building to the campus. We have elevations. ناقصل زي عمان جبال وأودية. فTickle, he said, you want to use my materials on the bridge as an advertisement for my work. The structural engineer, he said, I'm not signing for a bridge that use fiberglass materials. It's got to be concrete and steel. So the solution around it, you see these fiber composite materials, inside them, there are steel and concrete beams. So he refused that. And you see, these are very beautiful panels of fiberglass, but all of these structural elements, they are concrete and steel. So that brings my third point. We civil engineers, we need to think outside the box, and we need to transform our profession. And one advice try to design as if you are paying for the construction of your design. Because we owe it to people. You know, we should give them a design that's an economical design. And poorly educated engineers, they are the problem for our profession, really. If you are confident about your work, if I design a bridge, I'm confident, then I should be willing to stay or stand behind the bridge, even at the extreme events. If I'm not confident in doing that, I shouldn't be doing that design. And do not be afraid of failure, and have confidence in your skills. You cannot verge, or you cannot go to new things without kind of taking a risk. But it is not a risk ليس يعني مغامرة الجاهل ولكن مغامرة العالم. If your fundamentals are correct and you know what you are doing, you will be successful. So powering sensors, you know, going to the sensors, powering sensors is really a challenge. You know, on surface sensors, we can power them easily, but our foundation engineering is a kind of, you have buried sensors. So the soil or the concrete will kill the signal. But now the wireless sensors, they are coming, you know, coming into. So I think in the next 10 years, we will have a revolution in the technology here. Remember, the technology is a two-way edge, and we rely heavily on technology. But frankly, relying 100% on technology can be a very dangerous thing here. So here I'm showing you a video. I hope it will play. I think my video is gone. Yeah. I don't know how much I'm doing on time. Do I have time? Yeah. لا مو راح هو. حطوا هذا هو اللينك.
I think we should explore a few solutions.
Grammarly ensures your writing conveys.
Here's Jess.
Yeah, okay. If you play it and stay here until we finish it.
Jamie Jones.
Smoothie.
Making smoothie.
Calendar.
No meetings today. Remember and test at 9:30.
Fire off.
Fire off.
Open door.
Door open.
And we're going to do one more.
Open door.
Wrong voice command.
Open door.
Wrong voice command.
Open. Open door.
Repeat back.
Open door.
I didn't understand that.
Hey! Open door!
Play on the floor.
Thank you. So this is a very funny story, you know. These are, I call it luxury technology, but can put us in a big trap. We don't want to go that far, and we want to have engineered technology there. So I think what's next for our profession, if you go to this slide, please. Just go back. Just go back. about to finish. So what's next, you know, for our profession? I think the private industry and the research in academia and some of the federal labs, actually, they are making a major impact on civil engineering, although it's at a slow rate. I think a multidisciplinary team is more beneficial than just working with civil engineers. You know, for my research, I work with people from physics and material science, and that's really much better than just staying in your comfort zone. The 3D printed materials or additive manufacturing, it's just a matter of time, and it's coming and it's changing our profession. And there are really very good developments in that direction, and I think we will go in that direction. So here I'm showing you a development. Oak Ridge National Lab is in Knoxville, Tennessee, a Department of Energy lab. So Oak Ridge National Lab, they are doing full-scale 3D printing. So this is a house. This is a house fully powered by solar panels. It's not connected to any power source, and it has a vehicle also. This vehicle is 3D printed vehicle. So the house generates power and it stores it, and actually it can charge the vehicle itself. So this is a full-scale model they are doing it, so there's no need to play this. So as concluding remarks, I think we should start from the house. So as parents, we have really a challenging task to raise our kids. And my advice to young parents, try not to expose your kids to any technology before age 10. It's very hard to do that, but please, no cell phones, no all of this, because that's really, I'm talking about as an educator in academia, I think we need to change our curriculum to adapt to these new developments. We still teach the fundamentals, but we need to change the way we teach civil engineering. You know, humans usually resist change, and they want to stay in their comfort zone. And it will take a lot of pain and a lot of courage to make the changes. Civil engineers, I'm sorry to say that, I know some people surviving or heavily using concrete and steel. I think civil engineers, we need to minimize the use of concrete and steel. They are bad for the environment. You know, the concrete is a major source of CO2 emission and not good for our environment. And there are other materials we should adapt to. So 3D printing technology, it will change our profession. Self-driving cars, they will be on the roads in 10 years in some countries. And my advice to you as a last comment, be among transforming innovative leaders of the profession. These are some of the references. I would like to acknowledge the financial support from Louisiana Department of Transportation, Federal Highway Administration, and so also from my department and Tennessee Department of Transportation for the drones project. I invite you to visit us in Knoxville. This is a picture I took in the Great Smoky Mountains, the mostly visited park in the United States, very beautiful East Tennessee. So I'm extending the invitation to all of you to visit me, and shukran jazeelan lakum.
Well, thank you, Dr. Al-Shibli, for this excellent and remarkable presentation, which talks about structural health monitoring, enabling technologies, and of course the advices that has been sent by Dr. Al-Shibli at his final part of his speech. Now we will allow for a couple or three questions. Okay. We will start with Engineer Presharat. Please, go ahead.
Thank you for your lecture. I have been visiting the United States and Canada for the last 30 years, so many times. And I think the Americans, especially in those tornado areas, they know where it will hit and what is the route it will hit. I just wonder, as an outsider or just monitoring the system, why they don't force the people or rebuild their houses instead of wood to something else. They always have the same problem. They always have bad structures.
Yes.
They demolished homes. Everything is the same. For the last 100 years, so many repetition of building the same house, the same problem.
Same problem.
I just wonder why.
Well, yeah, I will tell you an example for that. United States is driven by the lobbyist. اللوبي في كل المجالات. فأضرب لك مثال. Even for these wood structures, if you just change the nails themselves from a regular nail to a nail with shear areas where this nail will take tension, will solve the majority of these tension on these structures. So when some people suggested just change the nails, put in the code that use new nails, who objected to that? Builders, contractors. They objected and they killed it. Why? Because if you tell them use new nails, that will add cost to them. And they lobbied against it and they killed it. I agree with you, and that's really the problem we have. What drives the United States is the money. Even the federal government lobbyists, legal lobbyists, they buy them. They buy them for this. So they do not do, and that's a problem, professional engineers, our suggestions most of the time get killed because of these things, unfortunately.
Bismillah ar-Rahman ar-Rahim. In Jordan, we have one of the main highway in Jordan is Irbid Amman Highway. I was director of the lab and research in the public work house, Ministry of Public Work. We made a monitoring system for the slide area because in this, you know this road.
Yeah.
We have many spots of land slides, and we monitoring these areas by مركز الجغرافي الأردني. I want to ask you, you speak about the drones. Use drones for monitoring. Can we use these plates and drones for monitoring these slide area in the future and make this system?
Yes, you can use target areas and fly the drones, take measurements of the targets, fly again and take measurements again. The one next to you, Jamal, is a slope stability expert.
السلام عليكم. شغال حاليا على 16 miles highway in West Virginia, which is mountainous like Irbid Amman Highway. We utilize LiDAR mapping either with drones or small airplanes monthly, so they can even keep track of cut and fill quantities and landslides. We have maybe a total of 10 landslides on the job, and we compare on a monthly basis the contours that we get. We see if they are moving or stopping. We used the health monitoring systems like what Dr. Khaled mentioned earlier with the major slide there that took place 3 years ago and still actually being fixed. So the drone technology and the LiDAR is very effective. Like for Amman, 28 years ago when I left this country, Amman was small. Now, I was surprised this morning, going through these nice high-rise buildings and all these. They are all also very close to each other. So with the geology that you have in Amman, there should be some way of monitoring these buildings, these roads, to make sure that a drone flight with some LiDAR surveying once every 6 months will give you an idea of these buildings, if they are getting closer or not. The major landslide that I've been working on, and Dr. Bashar knows about it, I keep in the loop, happened 3 years ago. They were building 2 piers 200 feet tall, and they are measuring center to center distance, and it's getting closer. So we had to put instruments, and we found out it's a major, almost 500 meter long landslide. So far, we spent $7 million just in instrumentation and studies to figure out the solution, which we did. And it's going to cost, in negotiation now, around $40 million just to fix that landslide. So this technology is very, very effective and cheap. Yeah. These 16 miles, we fly them every month, it costs $9,000, which is, for a $450 million project, is nothing.
Thank you. Okay, we will also for one more question. The lady there, please.
السلام عليكم. يعطيك العافية. بعد هالمحاضرة لازم التعليم عنا بالهندسة المدنية يقلب كليا يعني. هلا احنا كنا نصمم على الكونكريت والستيل والاشياء التقليدية، حاليا هاي الاشياء بطلت يعني مناسبة لهاي المونيتورينج. هلا سؤالي، لما كنتوا تشتغلوا على الجسر كان جسر رئيسي وكلف اخذ يعني وقت 7 سنين تقريبا منكم. هلا كانت تضغط عليكم الحكومة مثلا انه استعجلوا لانه بيأثر على الامور المالية للدولة مثلا؟ كم تكلفة المشروع تاعت الصيانة؟ هاي الامور اعطينا فكرة عنها.
والله هو تنفيذ الكونتراكتس في امريكا very slow للاسف. عندنا مشكله شورتج في الليبر، مع انه they pay very well for the construction. يجوز دكتور جمال بيعرف، بس عندنا very shortage في الليبر. Nobody wants to work in the construction. So it's very slow, but usually the contractors like the projects من DOTs لانه they pay them very well. I do not know exactly what is the budget for that bridge, but we executed it very fast in terms of this was finished a long time ago. So I think it took only a year and a half to finish back then. Nowadays, because of COVID, we have a huge shortage of labor there. Yeah. In terms of maintenance, they have the joints maintenance is a nightmare for the DOT. So they would rather pay a big cost up front and forget about it. So for them, maintenance is a major issue, because maintenance, they are very small contracts and very small jobs, and time consuming also. With so many bridges, they have to send inspectors, they inspect them, classify them, put them on maintenance schedule and stuff like that. Yeah. Yeah.
Any more questions?
السلام عليكم دكتور خالد. بنشكرك على الدعوة. أنا المهندس ياسر غنام لجنة المواد الإنشائية وضبط الجودة الشعب المدنية. بنشكرك على الدعوة لتينيسي. احنا بالعام 2017 2019 راح منا 10 زملاء حضروا مؤتمر الACI في تينيسي وفي لوس أنجلوس. سؤالي أنا بالنسبة للحساسات، جبت مثل على الجسر، هل في أوجه ثانية في مجالات الهندسة المدنية ممكن استعمال هاي الحساسات بحيث إنه يكون في فائدة منها؟
يا طبعا في يعني فيهم فوائد لكل الابلكيشنز. Yeah, I just gave one example, but the applications are huge in many. Yeah. The bridge inspection is the biggest thing actually. Yeah.
Bridge inspections, like when you have عندنا في الأوهايو ريفر long span bridges حوالي 2000 feet long 500 700 متر. Drones owned by the state or private,
the bridge, yeah.
they go through and they take very detailed 4K and 8K pictures now, so they can define if there is any cracks or there's any issues. They use it also on dams. Sometimes the inspection of a major bridge over these big rivers may take you 2 weeks if you have to do it manually, and a lot of cost. So they replace it with the drone very efficiently. Within a day they can be done, and it flies under, above, and it goes between all the structural elements and make detailed pictures. And now they have software available through the flight, like what Dr. Khaled showed, that it will give you a 3D image of the structure. And if there is any, especially in big steel structures, fatigue is an issue. So they can go through these high definition pictures and see if there is any cracks, micro cracks, and all that stuff. And so it's very effective.
And one more comment, actually, the latest iPhones, iPhone 14, it has a LiDAR in it itself. So with the iPhone itself, you can carry it with your hand and just scan an area, and you look at it immediately. It creates for you a 3-dimensional image of whatever you scan. So the technology is becoming really very handy. And I'll be happy to help anybody who wants to know about the drones later on. Just free of charge, just as a رد لعرفانكم يعني أهل الأردن. وشكرا جزيلا.
شكرا. بس very short question.
موظف.
Okay, this is a political question. This is a political question. Okay. At the end of the session, I would like to thank the speakers for their valuable and remarkable presentation. Dr. Sezen, Dr. Al-Shibli, and the thanks also is extended to all of you. Thank you very much, and thank for the organizers. Thank you very much.